So I have mailed a file, a small file containing two corrections. While discussing in our previous classes, there are some error found in the study material that I have mailed already to you. The first one was in page 17 in the couple circuit, the dot was placed in the wrong terminal. So that has been corrected. Okay, and earlier this was here. So it has been corrected, it should be here. I have explained this in our previous class. Okay, and accordingly the polarity of the mutually induced EMF, the source M23 DD2 DDG of I, that was also corrected here. Proper sign has been given. So this I have given you again for your reference. You may keep it with you. Okay. Those who have already noted this, it's all right, but at the same time we can keep it. Another was regarding the Norton's theorem application in this uh, circuit. Okay, we have found out the Thevenin's theorem, found the Thevenin equivalent and Thevenin impedance, and then proceeded to find out the Norton equivalent. So for Norton equivalent, what has to be done, this is the addition. And one more circuit I have introduced here in figure 21.7a. This was 21.7. Another figure 21.7a has been introduced, where basically to apply the Norton's theorem, you have to here a short circuit has to be placed. Okay, the short circuit has been placed here. Obviously, the current through this short circuited part is the Norton current. So let us assume that so actually the value of I1 was wrongly put in the previous note. So that correction has been made here. All right. So when this is IN, under this condition you have to find out the value of I1. So let us assume that this is I1. This current is I1. Obviously, this is the Norton current or short circuit current. So obviously Norton current will be equal to summation of this current and this current. So if it is IN, if it is I1, this current obviously will be IN minus I1, and the voltage across these two terminals will be same. So let us find out the voltage across this branch, which is V1 minus I1 into 1. Across this branch it is AV1 minus IN minus I1 into 1. So these two voltages are equal. From here you can find out the value of I1 in terms of IN, and then putting the value of, then this circuit has been obtained by converting this circuit into where the current voltage sources were converted to current sources, and then again current sources are converted to voltage sources to have this circuit. Because this circuit is somewhat easier. You can actually find out the value of IN from this figure also, no problem. You can find out, solve this. But since we have done this, from here you can find out the value of IN by putting the value of I1 from this expression. Put the value of I1, it will be V1 by 3 minus B, 1 plus A plus B minus A. So this is the correction. I have actually mailed to you this one also. So you can keep it as the correction of the original study material that I has given. Okay. Now with this, I shall proceed to the next topic. All right. Is there any question here up to this? The previous one was already discussed. Previous one was already done, and it was discussed. Perhaps some of you have noted this also. And there was some error. So this error has been checked here. Simply the value of I1 was wrongly put. The correction in the here. So this you can do, or you can actually find solution using any other technique. Somehow you have to find the value of IN in this circuit. That is required. Okay. Any question up to this? Any doubt?
Sir 21.78 আরেকবার বলবেন
21.7a here আমরা কি করছি, Norton equivalent. So what has to be done? So for basic circuit was this one. So in this circuit we shall have to
short circuit current
we shall have to find out the short circuit current here.
Hmm.
To find out the short circuit current here, we are shorting these two terminals. By shorting these two terminals, this is the circuit we obtain. Now, from this circuit, we can draw this one. So previously, this was not shown. Directly from this circuit, I have shown this one. Now we are showing this circuit as well. Now here you see that this current is IN, Norton current. আমরা যেটাকে বলছি, or I can the short circuit current basically is the Norton current. Since our aim is to find out the Norton equivalent, I am writing this as IN. Since here it is also IN. So if it is IN and this dependent source is given to be B times I1 when this current is I1. So let us assume that this current is I1. If this is I1 and this is IN, obviously the current through this branch will be IN minus I1 because summation of these two branch currents must be equal to IN. Okay, because this current will circulate like this current will circulate like this. They will, yeah, summation of these two will produce IN. So if this is I1, this branch current will be IN minus I1. Now, across these two terminals, these are the two branches connected in parallel. Obviously, their voltage across these two branches that is same. So you find out the voltage across this branch from the voltage and the current flowing through this impedance. From the voltage and current flowing through this impedance, this is the voltage across this branch. This is the voltage across this branch. They are equal. From this expression, you can find out from this equation, you can find out the value of I1 in terms of IN. Then again, by putting the value of IN here, you can now manipulate to find out the value of IN equal to V1 by 3 minus B, 1 plus A plus B minus AP. Okay, so simply it was V1 by 3, it is actually minus B. Okay, so this is the correction you made. Calculate this again. You solve the circuit using any other technique, or what you can do, you can simply apply loop analysis to solve the current in this circuit, find out IN, find out I1. So IN will be equal to the Norton current. Okay.
Okay, sir.
All right.
Yes, sir.
Okay. Then let me move to the for further discussion. Let us this one.
So one student is not able to join. So
Actually, এত দেরি করছে এরা। একটু আগে এলে হয় কি তখন এটা সুবিধা হয়। Okay, you try to, all of you, please try to join earlier. Then I can start in time. Okay, otherwise what happens? Somebody is entering within the class, I cannot see him or her. Then you have to tell that somebody is trying to join. So in this process, someone may actually not be able to join also because if I am not informed, I cannot admit him. Okay, so please try to join timely. Okay, all right. So then, where we are in the original study material, let us go there. Uh, I've done these things. The correction was introduced, and this was also done. This is done. Okay, now we shall start at page number 25 with some examples on the application of uh, network theorems. Okay, a simple problem is given here. So this is a resistive network shown. In this network shown, resistive network means obviously it will be linear network. Okay, linear network. We have a current source at the input terminals and a voltage source at the output terminals. That voltage source is connected with therefore the resistance. Okay. This current is shown to be small I, and this current source current is the capital I. Okay. Now some conditions are given, measurement conditions are given. It is given that number one, when E, that is this voltage source, is made equal to 4 volt and I, current source value is 2 ampere, and this resistance at the output external to this resistive network and since it is with the voltage source, when it is equal to 2 ohm, then current flowing to the source here, this current becomes equal to 0. Okay, that means this is equal to 4 volt, this current source value equal to 2 ampere, resistance is 2 ohm, then under this condition, this I becomes equal to 0. This is the condition 1 given. Second condition given is E is made 8 volt, I is maintained at 2 ampere, R is 2 ohms, then this I now becomes equal to 1 ampere. So this is the two measurements given. Now from these measurements, you have to determine something such that finally you have to find the value of I when this E is equal to, this E equal to 8 volt, I is minus 4 amperes. Reverse polarity is reversed for this source now. I is minus 4 ampere and R is made 4 ohm. So this is the problem. Okay. So solution is already done here. It is given. Now let us see whether you could understand all this or not. Now, what you can determine from the first condition. You see here, this is 4 volt. This is 2 ampere. That means when this source is equal to 4 volt, this source is equal to 2 ampere, and R becomes 2 ohm, then this I becomes 0 ampere. That means no current is flowing here. So when this E is equal to 4 volt. All right. So what you can observe, what you can know from this condition? Anybody? It is given here. Since I is equal. Anybody who is speaking?
এখানে স্যার মানে এটা I is equal to 0 আছে মিন্স মানে হচ্ছে ওপেন মানে হচ্ছে ওপেন ওপেন যে টার্মিনালের যে ভোল্টেজটা ওটা ওটা যে 4 ভোল্ট
ওটা 4 ভোল্ট অর্থাৎ কি হচ্ছে I equal to 0 মানে হচ্ছে এখানে এখনো কারেন্ট ফ্লো করতে পারছে না নো কারেন্ট ক্যান ফ্লো ইন দিস সার্কিট and when this is possible when from this resistive network a voltage equal to this source voltage is appearing here. That means another voltage with 4 volt magnitude with positive polarity here and negative polarity here is appearing, okay, because of this resistive network along with this current source. তাতে করে কি হচ্ছে when this source is equal to 4 volt, it cannot drive any current or no current is flowing from this network to this external load, external resistance R. That means at the two ends of the resistance, voltage is 4 volt here, voltage is 4 volt here, such that through this resistance no current is flowing. Is it clear? That means it indicates that if I open these terminals, open this source from here, then what will be the voltage available here? It will be, what will be the voltage available here? It will be 4 volt. Because since it is 4 volt here and 4 volt here, no current is flowing through this branch. Okay, that means open circuit voltage at the output terminal is equal to 4 volt. Or we can say that we may say that for this total network, left of this resistance, you can say this part, resistive network along with the current source. This may be represented by a Thevenin voltage of 4 volt. That means we are in a position to determine the Thevenin equivalent of this total network to the left of this resistance R. Is it clear? That means we may determine the Thevenin equivalent because Thevenin voltage is very much given here. How? Indirectly this is given. You have to read that this is the Thevenin voltage. How you can read? Because this voltage, when this voltage is 4 volt, no current is flowing, means when this is 4 volt, no current is flowing. Meaning of this is 4 voltage is available here also. That's why through this resistance, no current is flowing. So Thevenin voltage to the left of this terminals is equal to 4 volt. Okay, so from the first condition, we can obtain the Thevenin voltage of the network left of this resistance R. Okay, now to represent this, we have to determine the Thevenin impedance as well. Then only we can find out the value of the current flowing through this external circuit when 8 volt is this E is made equal to 8 volt and current source value is made equal to 4 ampere. Because we don't know the value of this, why you have to find out this? Because the resistive network, you said that there is a resistive network, but nothing is given about this resistive network. What are the resistances, how they are connected, these things are not given. But an information is given in measurement condition 1 from where we can say that V Thevenin here, open circuit voltage here will be 4. All right. Now let us find out, let us see whether from condition 2 we can find out the Thevenin impedance or not. What is given?
স্যার
When it, bolo.
স্যার একজন ঢুকতে পারছে না, সৌগত মিস্ত্রি নামে, ওকে একটু অ্যাডমিট করে নিন না।
All right. Okay. Then, all right. So, when you see condition 2, here E is 8 volt. This is 8 volt. I becomes equal to I is 2 ampere and R equal to 2 ohms. I becomes now 1 ampere. From this condition, what you can determine? This is 8 volt. Okay. I remains 2 ampere. Tarmaniki, when I is equal to 2 ampere, we have seen that from the first condition, when I was 2 ampere, R 2 ohms, okay, then current was 0. Now also I becomes or remains 2 ampere. That means the Thevenin voltage here is not changing, it will remain same because the network is linear network. There is no other sources inside, sources are here only. Okay, so this source remains unchanged means the Thevenin voltage at the output terminal also remains unchanged. That means Thevenin voltage becomes 4 volt here. Okay, it remains 4 volt here. So when it is 4 volt, E is made 8 volt.
স্যার একটু আগেরটা একটু রিপিট করবেন স্যার।
ঠিক আছে, ফার্স্ট কন্ডিশন কুড ইউ আন্ডারস্ট্যান্ড?
ইয়েস স্যার।
কন্ডিশন 1 কি আরেকবার এক্সপ্লেইন করব?
না স্যার এটা ঠিক আছে।
আচ্ছা, কন্ডিশন 1 টা আবার বলছি যে ইন কন্ডিশন 1 this voltage is given, I is given to be 2 ampere, R is 2 ohm and I is 0. আমাদের কি করতে হবে? বেসিক্যালি we shall have to know this resistive network. What is the composition of this resistive network? আমরা তো total number of branches, resistance, তার composition, তার connection যদি না জানি, obviously we cannot find out the equivalent. তাহলে somehow কিছু একটা information দরকার so that we can obtain the equivalent value of this resistive network. That equivalent value we may obtain in the form of Thevenin equivalent. You have a current, you see that here it is given that this current I becomes 0 when a 4 volt source is connected here and I becomes 2 ampere. This means that when this I is 2 ampere, a voltage equal to 4 volt is appearing across the output terminals. So that because of this 4 volt here and 4 volt here, no current is flowing through this resistance or through this path. At the output terminals, voltage becomes equal to 4 volt, or you can say that Thevenin voltage equal to 4 volt. Okay, that's why you can see that this total network may be represented by its Thevenin equivalent, where already we know the Thevenin voltage, which is 4 volt. Now we shall have to attempt to determine the Thevenin impedance. Okay, let us now see whether from condition 2 we can find out Thevenin impedance or not. What is given in the condition 2? In condition 2, I remains 2 ampere. Okay, that means previously also it was 2 ampere, now also it is 2 ampere. R is same, it is the external resistance, it is same, and I becomes 1 ampere. Okay, now some current is flowing. 8 volt is the voltage with the value of source here. That means when this is 8 volt, this remains to be 2 ampere, then this is the current I, which is equal to 1 ampere now. Under this condition, আমি বলতে পারি, since this current source value remains unchanged, Thevenin voltage here also or open circuit voltage here also will remain unchanged. Okay.
Yes.
This is a resistive network. So in resistive network, if there is a change in this source, then only there will be some changes in the output voltage. Since there is no change, here also there will be no change. That means Thevenin voltage here, because of this current source, 2 ampere current, here the voltage will remain to be same as before, which is 4 volt. So we know that the value of voltage is 4 volt. Now, from condition 2, this E is equal to 8 volt. So আমি কি করতে পারি, this total network is creating a voltage equal to 4 volt here. So here the voltage is 8 volt, voltage source voltage is 8 volt. This resistance is given to be 2 ampere. So this is R cell. Okay. Now we don't know the value of the Thevenin voltage. The total network may be represented by a Thevenin equivalent, means a Thevenin voltage plus a Thevenin impedance. Say that impedance is Ri, internal impedance of the network, say Ri. So we can say this 8 volt minus Thevenin voltage here divided by R plus Ri, because this total thing will be replaced by the voltage source, Thevenin voltage plus series impedance. That series impedance is Ri. So current will be E minus Thevenin voltage divided by R plus Ri. That is written here, and that is given to be 1 ampere. Is it clear?
Yes, sir.
Everybody, it is clear? Alright, বুঝতে পেরেছো? Anybody having any doubt?
No, sir.
Okay, so it is 1 ampere. So if it is 1 ampere, your value of R is known to you, Thevenin is known to you, so you can find out Ri, which is 2 ohm. Okay, so from here we can find out the value of Ri, which is 2 ohm. Now you represent the network by Thevenin equivalent, Thevenin plus Ri. Ri is already determined 2 ohm. Okay, and here this is R, this is E. You have to find out the current I under this condition when E is equal to 8 volt. E is 8 volt. R is 4 ohm. This R is made equal to 4 ohm, but this current I becomes minus 4 ampere. That means now this current I is made equal to minus 4 ampere. Previously, when this current was equal to 2 ampere in this direction, 2 ampere pass, then a voltage equal to 4 volt was appearing across the output terminals. Now, when this current is made equal to minus 4 ampere, that means its value will be multiplied. It will be twice. That means it will be 4 volt. Ultimately, it will be 8 volt twice. It will be 8 volt, and its polarity will be reversed because the current value at the input is also reversing. So this Thevenin voltage now will be equal to minus 8 volt. Okay, it is V Thevenin, positive polarity and negative polarity is shown as given here, but value of V Thevenin will now be equal to minus 8 volt. Why minus 8 volt? Because current value becomes minus 4 ampere. Previously it was plus 2 ampere. When it is becoming minus, polarity will be reversed. When it becomes 4 ampere, magnitude will be double. That's why with 2 ampere current, voltage was equal to 4 volt. With 4 ampere current, voltage will be equal to minus 8 volt. So minus 8 volt with negative polarity here, positive polarity here. Now in this circuit, negative, positive, here negative, positive, that means 8 and 8 they are in series. So 8 plus 8 divided by 2 plus 4. 2 plus 4, ultimately current is 8 by 3 ampere. Is it clear or not? See.
Sir, can you explain how the magnitude of VTH is doubling when I is doubling?
VTH I is doubling because the network is resistive network. Resistive network means resistance is linear. What we assume is that is actually what will happen if the current flows through resistance. Then depending on the material used, there will be some changes in the resistance value. But change in the resistance value, if it is very small, we may consider that resistance to be constant. And the network with resistance generally will be linear network. That's why we are assuming that the network is resistance means it is a linear network. In linear network, if the input voltage is doubled, output input current is doubled, current source value. Say if it is double, voltage measured here also will be doubled. If it is 5 times, voltage of ampere current here was producing a voltage of 4 volt at the output terminals. So 4 ampere current will produce a voltage of 8 volt with positive polarity here and negative polarity here. That means current value when it is plus 2 ampere, obviously positive terminal of the current source is here at the arrowhead, negative terminal is here. So with current value becoming minus 4 ampere, obviously here also the polarity of the voltage will be changed. Previously it was plus here, minus here. Now with I equal to minus 4 ampere, it will be reverse, plus here at the bottom, minus here at the top. Is it clear now?
Yes, sir.
Any doubt, anybody?
Sir, can you please repeat why if R equals to 2 ohm, Ri will be 2 ohm?
Huh. That we have found out from the second condition. When R equal to 2 ohm, why Ri is 2 ohm. Okay, Ri means internal resistance. Internal resistance basically how we are representing the equivalent of this network. We are representing it in the form of a Thevenin equivalent, means Thevenin voltage with Thevenin impedance in series. That means this total network is represented by a voltage source with series impedance. That series impedance is equal to Ri. All right. So if you put this in the second condition, when this E is made 8 volt, I remains 2 ampere and R is 2 ohm. তার মানে তুমি এখন কি করবে? You see that here how I can represent the network here between these two terminals with the help of a voltage source of 4 volt and series impedance say Ri. That means this is represented by a voltage source of 4 volt with series impedance Ri. Now, current is known to be 1 ampere. So what is 1 ampere current? This is this voltage minus this voltage. So it is 8 volt minus, what is the voltage here? It is V Thevenin. So 8 volt minus V Thevenin divided by this external resistance R plus series resistance here, that is equal to Ri. So 8 volt minus 4 volt divided by R plus Ri, that is equal to 1 ampere. This is a condition given. Okay, this condition was given. We have actually used this condition to write this expression. So when you write this expression, now you can find out the value of R because so the value of Ri, because R is given to be 2 ohm. Put the value of R. V Thevenin already we have determined 4 volt. So write the value of V Thevenin here, put the value of R here, find out the Ri, that is. Is it clear? Would you understand?
Yes,
Is
sir.
the question? Okay, is it clear? So may I proceed now further? Okay.
Yes, sir.
So let us now move on to the next. Another simple example we are considering here, that is also very simple. Here, a 1 ampere current source connected at the input terminals of a linear network produces a potential difference of 6 volt at the output terminals. Okay, so imagine a network. Okay, that not what is that network, that is not given. The details of the network is not given. So you consider a network like this within a you consider a box like this. Within there, inside this there is a network, and at the current input, a current source like this is connected. Okay, so 1 ampere current source connected at the input terminals of a linear network, okay, produces a potential difference of 6 volt at the output terminals. So in this linear network here, when 1 ampere current source is obtained, is connected, a potential difference here of 6 volt appears at the output. Okay. a potential difference of 6 volts appears at the output terminal. Immediately you can say that for that network with 1 ampere at the input, 6 volt is the potential
Thevenin
at the
voltage.
output, means 6 volt is the Thevenin voltage. Right? 6 volt is the open circuit voltage, means Thevenin voltage. Okay. Now, when the output terminals are connected to a 10 ohm resistance, now a 10 ohm resistance is connected at the output terminals. Okay. So this we can represent that network by 6 volt in series with Thevenin impedance, Thevenin's resistance. What is the Thevenin resistance? Not yet known to us. We have to find it out. Okay. That's in linear network with 1 ampere current source at the input may be represented by a 6 volt source with series impedance of say R Thevenin using Thevenin's theorem. Why we say that you can use the Thevenin's theorem? Because under the condition of 1 ampere current source at the input, output terminal V potential difference becomes 6 volt. Meaning is that the open circuit voltage at the output terminal is 6 volt. That's why, since that can be identified to be the Thevenin voltage of this network, we say that we can represent this with the help of Thevenin equivalent, and that Thevenin voltage is known. That is equal to 6 volt. And let us assume that R Thevenin is the Thevenin impedance. Okay, that means the series impedance. Now, what happens when output terminals are connected to a 10 ohm resistance? Now, here you are connecting the output terminals through a 10 ohm resistance. Here is connected. The potential difference drops to 4 volt. Now, what happens at the output? Okay, we are basically this R Thevenin. This is inside the network. You cannot get it outside. We are showing it here at the equivalent. But what happens when a 10 ohm source is connected to output and you measure the potential difference at the output, that becomes 4 volt. Previously, it was open. So between the open circuit terminal, we can see. Now, as soon as you connect 10 ohm across the two terminals, the reading of the voltmeter becomes 4 volt. It drops to 4 volt from 6 volt. Would you understand the statement of the problem here? When the output terminals are connected to a 10 ohm resistor, the potential difference drops to 4 volt. All right, that means this is the situation. This was the output terminals. Previously, it was open, so you got 6 volt. So this 6 volt, because no current was flowing at the output, was obtained here. Now, this R Thevenin is internal to the network. We are showing it here, but this basically is internal to the network. These are the output terminal. Between these two terminals, we are connecting a resistance of 10 ohm. As soon as you connect a resistance of 10 ohm, you see that potential difference here. That means the reading of the voltmeter across the two terminals drops to 4 volt. All right. So where the remaining 2 volts go? Where the remaining 2 volts is going?
Across the internal resistance, sir.
Across the internal resistance. That means as soon as you connecting the 10 ohm resistance here, now a current may flow through the circuit. And because the current is flowing, there will be a voltage drop across this 10 ohm resistance. Voltage drop is 4 volt. So remaining voltage is being dropped across the internal resistance. So we can say that across the 10 ohm, since the voltage is 4 volt, remaining 2 volt will appear across the internal impedance. So 4 volt appears across 10 ohm. So 2 volt, and 2 volts will be appearing across 50% of this resistance. When it should be 5 ohm, isn't it? That means since 4 volts appears across 10 ohm resistance, certainly if you consider a series circuit, the voltage drop across the internal resistance has to be 2 volt, because the total voltage was 6 volts. 4 voltage is dropped here. That means the remaining voltage is dropped across the internal resistance. So across 10 ohm, if the drop is 4 volt, 2 volt will drop across 5 ohms. That's why Thevenin impedance is 5 ohm. Is it clear? Why Thevenin impedance is written to be 5 ohms?
স্যার এটা আরেকবার বলবেন?
হ্যাঁ, ব্যাপারটা কি হচ্ছে যে দেখো, first part I think it is clear that 6
Yes, sir.
volt is obtained at the output terminals, and we are writing that 6 volt as the Thevenin voltage. I think that part is clear.
Yes, sir. Yes, sir.
Now, what happens? That part now we are representing by this equivalent 6 volt with R Thevenin as the series impedance. Now we assume that these two are the action term. Actually, it would have been better had I shown a terminal here, terminal here. এটা করলে দিলে ভালো হতো আর কি, এক্সপ্লেন করতে সহজ। Okay, so there is a terminal here, there is a terminal here. These are the output terminals. So across the output terminals, now you are connecting a 10 ohm resistance. And as you connect the 10 ohm resistance, you see that the potential difference across the output terminal drops to 4 volt. তার মানে কি হচ্ছে, remaining 2 volts is actually dropped across the internal resistance, তাই না? If 4 volt is dropped across the output resistance 10 ohm that is connected across the output terminals, obviously remaining 2 volts, where has it gone? Obviously it has dropped somewhere. Where it has dropped? It has dropped across the across the internal impedance of the source. Previously, when the terminals were open, the total voltage was obtained here. Because then no current was flowing. Why no current was flowing? Because the terminals were open. That's why no current was flowing. Now, as you are connecting the 10 ohm or 10 ohm resistance across the output terminals, a current is flowing, and because of that current flow, there is a voltage drop across the internal resistance, and that voltage drop is equal to 2 volt. Am I clear?
Yes, sir.
Is it clear to everybody? So you see that from here we can find out, we can identify that R Thevenin is 5 ohm. Okay, if this R Thevenin is 5 ohm, now we can draw this circuit. It is 5 ohm here. Now some question is given here. Okay, estimate the current that would flow if a resistance of 20 ohm be connected across the output terminals when a 2 ampere current source is connected at the input. Now the input current is changed. Input current previously was 1 ampere. Now it has been made to, it will make 2 ampere. So if the input current is doubled, what will happen to the Thevenin voltage of a linear circuit? It also will become double. Double means it will be 12 volt now. Now that voltage become 12 volt, but the Thevenin resistance remains changed. It will not depend upon the current value because the linear network, that means the internal impedance will remain unchanged. Am I clear? So only the Thevenin voltage changes because of the change in the internal input source current. The Thevenin resistance remains same. Now you have connected a 20 resistance across the output. So now it is very easy. 12 volt source, 5 ohm here, 20 ohm here. Find out the current. This is 12 by 5 plus 25 means 12 by 25 ampere. 0.48 ampere, 12 by 25 ampere. Is it clear?
Yes, sir.
Clear, everybody? Any doubt, anybody? Please make the raise your doubt so that it can be made clear here. Okay. All right.
স্যার আরেকবার বলবেন?
আচ্ছা, আরেকবার বলছি তাহলে। তো আবার দেখো আমরা এক্সাম্পলটা আরেকবার রিড আউট করছি। এই 1 ampere কারেন্ট সোর্স, হ্যাঁ বলো। Who was saying something was being said? কিছু বলছিলে কেউ? A 1 ampere current source connected at the input terminals of a linear network. Note this, linear network produces a potential difference of 6 volt. What is the meaning of this linear network? Meaning is that in the linear network, the impedance value will remain unchanged. Okay. If there is a change in the input voltage or input current, accordingly the output voltage or output current will change proportionately to change. So a 1 ampere current source at the input is producing a 6 volt at the output terminals. If the current source is made 12 ampere, it will 2 ampere, it will be 12 volt at the output. If the current source is made 3 ampere, it will be 18 volt at the output. This is the meaning. Now in this network, from this first statement, what we can do, we can identify that at the output terminals, open circuit voltage is 6 volt. Meaning is that if we want to represent that network, linear network or resistive network, with the help of Thevenin equivalent, the Thevenin voltage is already known to us. It is 6 volt. So let us represent, it is known to us, let us represent the network with the help of Thevenin equivalent. So of that Thevenin equivalent, 6 volt is the open circuit voltage with 1 ampere at the input. Let us assume that R Thevenin is the internal impedance. Okay, so this is the representation of the equivalent representation of the network. Now what is done when the output terminals are connected to a 10 ohm resistance? Now a 10 ohm resistance is connected at the output, and it is observed that potential difference, which was previously 6 volt, now becomes 4 volt. Now you have to realize the situation here. If this is 4 volt is available here, obviously 2 volt has been dropped in the internal resistance of the network. The question is why there was no internal drop previously? Because previously there is no circuit, closed circuit produced at the output. That's why no current was flowing. Now a closed circuit is produced, a closed path is produced, so current is flowing. Because of the current flow, there is a voltage drop of 2 volt internal to the network. That's why at the output you are getting 4. So we can say that internal impedance of the source or internal impedance of the network, or which is the Thevenin impedance, is equal to 5 ohm. Why 5 ohm? Because across 10 ohm voltage drop is 4 volt. So 2 volts will be dropped across a resistance whose value is 5. 50% of this, that means whose value is 5 ohm. That's why R Thevenin we can write to be 5 ohm. Now when this is obtained, this is the 5 ohm resistance, internal resistance of Thevenin equivalent resistance. Now a question is given, estimate the current that would flow if a resistance of 20 ohm be connected across the output terminals when a 2 ampere current source is connected at the input. Previously current was 1 ampere, now it is made 2 ampere. So as it is made 2 ampere, obviously Thevenin equivalent voltage also will become twice. For 1 ampere voltage was 6 volt, for 2 ampere voltage will be 12 volts. So now therefore it is 12 volt. 5 ohm is the internal impedance, and now you have connected 20 ohm across the output terminals. So current now flowing in the circuit 20 ohm resistance will be 12 by 5 plus 20. This is the current. Is it clear now? Yes.
Yes, sir.
All right. Now let us move on to the next page, page number 26, where we shall be discussing reciprocity theorem. Have you studied reciprocity theorem earlier? Have you studied reciprocity theorem in the first year classes?
No, sir.
Reciprocity. It was not done, na?
Yes, sir.
Huh? Not
Sir,
done
it was
or
not done.
No, sir, it was not.
No, sir, not. It was not done, sir.
not done. What the reciprocity is, theorem states that the statement, let us read out this statement, it will be then easy to clear, it to explain. A linear network is said to be reciprocal or bilateral if it remains invariant due to the interchange of the position of the source and its response in the network. Okay, this is the statement. If we explain it with the help of a simple example, then you say consider a simple network, say consisting of two loops. Let us consider a simple network consisting of two loops. Let us actually এটা আঁকলে ভালো হতো. Let us assume a network. I am going up to find out a network of this one. Okay. So this consider this one. I shall explain this with the help of this network. So here you see that a 1 volt source is connected here. These are the resistances. Okay. Now what the reciprocity theorem states that if you change the position of the source and response, source is say 1 volt here, and response as a response, let us find out the current through this 8 ohm resistance here. This is the response. How? Let us connect an ammeter here. Okay, so 1 volt source is connected here, placed here, and we shall be measuring the current here. What will be the current if you measure? You can find out this current. What will be this current? It will be
Sir, I
Can you
by 3.
calculate? Eh?
I by 3.
I by 3. No, not in terms of I. You find out the actual value. What will be the current here through the 8 ohm resistance? I shall be putting an ammeter in series with 10 ohm, 8 ohm here.
1 by 11. 1 by 11.
1 by
1
11.
by 11.
1 by 11. Now, what you do? Let us connect the ammeter in place of the 1 volt source and shift the 1 volt source in the position of the ammeter. Say 1 volt source now will be connected here. Okay, in series with 8 ohm, and the ammeter will be here. So under this condition, what will be the current? Under this, could I make it clear? That means now it is 1 volt source is connected here. We have measured the current through 8 ohm resistance. How to measure the current? We had connected as if an ammeter here in series with 8 ohm resistance. So you calculated the current, that is 1 upon 11 ampere. Now you shift the ammeter from here to the position of the source and shift the source from this position to the position of the ammeter where it was previously here. I am interchanging the position of the source and response. Previous response was the current through branch 8 ohm resistance. Now the source will be placed here, response I shall measure here. So by placing the voltage source or 1 volt source in series with 8 ohm resistance, what will be the current flowing through this branch 1 ohm resistance?
1 by 11 ampere.
1 by 11 ampere.
It will be same.
Will be same. You see that previously here the current was 1 by 11 when source was here. Now if you place the source here, here current becomes at the position of the 1 volt source, current becomes 1 by 11. That means you are changing the position of the source and response. Originally this is the position of the source. You measuring the current here, that means the response here, that is 1 upon 11. The next time you have put the voltage source in series with 8 ohm resistance here and measuring the current in the position of the 1 volt source. Okay, so you see that current is 1 upon 11. That means changing the position of by changing the position of the source and response, there is no change in the value of the response if the value of the magnitude of the source remains same. That means what we can say, in this type of network, that is for those type of network where you can change the position of the source and response, those networks are known to be reciprocal network or bilateral network. This is the statement. That means a network is said to be reciprocal or bilateral if you can change the position of the source and response. Could you understand? That means in a reciprocal network, you can change the position of the source and response. If the magnitude of the source remains same, response value also will remains. Okay. And a network where you can change the position of the source and response without any change in the value of the response. If there is no change in the value of the source, then those networks are known to be reciprocal network. And this is the reciprocity theorem. Am I clear? Is it clear? The statement, is it clear? That means you can change the position of the source and response in a reciprocal network or in a network where you can change the position of the source and response. That network is known to be reciprocal. Okay, this is the reciprocity theorem. Okay, this is the statement. You said a linear network is said to be reciprocal or bilateral if it remains invariant due to the interchange of the position of the source and response in the network. I have changed the position of the source and response. The change of this position. That means since I have not changed the magnitude of the source, I have kept it constant. Response value, that means current value. আমাদের বেলায় source ছিল কি voltage ছিল, response was current, so response value also remains unchanged. Am I clear? And this is reciprocity theorem. Okay. That means in a linear network, linear bilateral network, this reciprocity theorem will hold good. You can easily change the interchange the position of the source and response without any change in the value of the response, provided the source value remains unchanged. Okay, is it clear?
Yes.
Okay, now let us discuss this theorem. Actually, this theorem was supposed to be completed in the first year classes. Since this was not done, uh, this is not done because of time problem, perhaps. Okay, so now make it clear, very clear, because it will be necessary. Reciprocity is a very important property of linear network. Okay, it will be used in future many times. You will see the application of this. Okay, it has to be very much clear to you. Now you see that we want to investigate this property in the context of the present discussion when we are actually analyzing the network using loop analysis, nodal analysis. Okay, what we have done, loop analysis and nodal analysis. Finally, we have written equation in the form of, say, in the loop analysis, we have written Z into I equal to V. What is Z? Z is the loop impedance matrix. I is the loop current vector and V is the voltage source in the loop. Okay. Also, we have written the equation Y into V equal to I. Just একটু আগে আমরা যেটা কয়েকদিন আগে যেটা দেখেছিলাম, Y into V equal to I. Y is the nodal admittance matrix, V is the node voltage vector, I is the injected current at the node. তাহলে এই যে নেটওয়ার্ক একটা ছিল, that for that network we have written expression in terms of admittance matrix into voltage vector equal to current, injected current. Also, we have written the impedance matrix, loop impedance matrix into current, loop current equal to voltage sources in the loops. এইভাবে লিখেছিলাম। তাহলে এই ইম্পিডেন্স ম্যাট্রিক্স অথবা অ্যাডমিটেন্স ম্যাট্রিক্স অথবা লুপ ইম্পিডেন্স ম্যাট্রিক্স অর নোডাল অ্যাডমিটেন্স ম্যাট্রিক্স আমরা এগুলোকে বলতে পারি দিস ইজ দ্য ম্যাথামেটিক্যাল মডেল অফ দ্য নেটওয়ার্ক। এটা আমরা এই জেড দিয়ে পুরো নেটওয়ার্ককে এক্সপ্লেন করছি। আমরা যখন জেড লিখে ফেলছি তখন আর নেটওয়ার্কের কানেকশন নিয়ে আমরা খুব একটা বদার করছি না, কি কানেকশন ছিল ছিল, বাট আই হ্যাভ রিটেন দ্য loop equation means basically that network is transformed or the network is translated in the form of this equation Z into I equal to V or Y into V equal to I. তাহলে basically nodal admittance matrix and loop impedance matrix, these are the mathematical model of the network. Okay, যাই কানেকশন থাকুক, ultimately value of the impedances are obtained. You have formed the loop impedance matrix, you have formed the nodal admittance matrix. That means you have represented the network with the help of this impedance matrix or admittance matrix. Now, let us investigate the property of the reciprocal network with in terms of the this mathematical model, in terms of the loop impedance matrix and loop nodal admittance matrix. Okay, now consider a network having only one driving voltage source equal to A. Okay, and say in the loop K and current response to loop M. We are discussing reciprocity theorem. So assume that we have a network, and in that network, let us assume that there is only one driving voltage source at loop K. Say this network is having a number of loops. Out of these loops, only in loop K there is a voltage source, and that source is equal to EK. And that is magnitude is equal to E. At loop K, say the voltage source is represented by EK, its magnitude is say E. Okay, in loop K. And say let us find out the loop current at loop M. So there is a source, voltage source in loop K. We shall be finding out the current in loop M. I want to find out the current in loop M. So this J, I can write this equation Z into I, loop impedance matrix, this Z matrix into loop current vector equal to loop voltage. Okay, since there is a single source at loop K, we have this source as K, loop voltage equal to K, EK, and all other loops are having zero voltage because there are no voltage sources, zero voltage. But because of this loop source at loop K, current will be there in each and every loop. because all loops are closed path, so current will flow. How we can write the expression of that current? I can write, say, what I can write? I can write this Z multiplied by I is equal to 0. That means Z11 I1 plus Z12 I2 plus Z13 I3 Z1K IK plus Z1M IM equal to 0. This type of expression I can write. Okay. Similarly, I can write ZK1 IK. In this way, I can write expression. Now, let us find out the current I. So, if I find the current I, what has to be done? This current vector I has to be determined. So, what we have to do? We have to pre-multiply this matrix by inverse of Z. Okay. Or we can say that this current vector will be Z inverse into this vector. Z inverse into this vector. Inverse of this matrix multiplied by this vector. Okay, is it clear? Because if you pre-multiply this matrix by Z inverse and pre-multiply this by Z inverse, then pre-multiplying this ultimately it will be unity matrix and you will get this one. Okay, that means loop current vector will be equal to inverse of the loop impedance matrix into loop voltage vector. Say inverse of the loop impedance matrix is written in terms of OI. So we have Y11 to Y1N, Y1M say, Y21, Y22. This way we can write the total loop equation and say we are finding the current IM. Then what will be the current IM? Current IM will be corresponding to the mth row. In the mth row, admittance is YM1 V1, it is 0, plus Ym2 V2, that is also 0, plus Ym3 V3, this is also 0, plus Ymk into Ek. Ek has a value. So Ymk into Ek plus Ym say n into En plus Ymm into Em. So all are 0 except Ek. So we shall have the term Ymk into Ek only. So Im will be Ymk into Ek. So in this expression, see all other terms on the right hand side except the kth row is 0 means you can find out the current value Im as Ymk into Ek. Okay, Ymk into Ek. That is what we can write. Is it clear? So if you can write this, that means I am writing Im in terms of Ymk into Ek. What is this Y? Y basically is obtained by taking the inverse of this Z matrix. Okay, and Ymk means mth row kth term, kth column of the inverse matrix. Z inverse mth row and kth column, that is Ymk. So from that I can find out the value of Im as this admittance element into Ek. Okay. All right, now you interchange the position of the source and response in that network. Now we shall put the source in loop M and measure the current in loop K. Previously, a source was placed in kth loop, current was measured in mth loop. Okay, mth loop current was measured. Now we shall put a source in mth loop and measure the current in kth loop. So the same expression you'll be writing here. Source will be placed in mth row because mth loop has a source, that is Em. So if you write the current expression now, kth loop current will be Ykm into Em because all other voltages are 0. So it is Ykm into Em. Okay. Now, if the network is reciprocal, okay, if the network is reciprocal, if the network is linear, then we can say that Im will be equal to Ik because as per the reciprocity theorem, you can interchange the position of the source and response, and therefore source will not change, response will not change so long as there is no change in the value of the source. So say we have kept the value of the source same, E here. So Ik will be equal to Im. If Ik and Im they are equal, Yeah, and if we keep voltages are equal, so we can say that YMK will be equal to YKM. YMK equal to YKM. That means in a reciprocal network, that means a network that follows reciprocity theorem, you can say that the admittance matrix will be symmetric. In a matrix, in the admittance matrix, YMK is equal to YKM. It indicates that the admittance matrix is symmetric. Is it clear? The admittance matrix is symmetric. That means for a reciprocal network, the admittance matrix will be symmetric. That means basically, if the Lenoir network is passive, sources are connected external to the network. If the network elements are having passive elements, okay, that means if there is no control sources and all these things, then you see that already we have seen that the admittance matrix becomes symmetric. That means those admittance matrices which are symmetric are basically the reciprocal network. Okay, they are linear and bilateral. This is the reciprocity. Is it clear or not? Okay.
স্যার লাস্ট লাইনটা আরেকবার একটু এক্সপ্লেন করবেন?
লাস্ট লাইনটা তো এই লাইনটা তো
হ্যাঁ।
এখানে
Yes.
না আমি যা বললাম সেটা
স্যার এই তো এখান থেকে আপনি যেটা বললেন
এখান থেকে আচ্ছা ওকে আমরা কি বলছি দেখো প্রথমে আমরা কি ধরলাম আমরা একটা সিম্পল নেটওয়ার্ক ধরেছি and let us assume that we want to see the property of the impedance matrix অর্থাৎ রেসিপ্রোসিটি থিওরেমটা কি সেটা আমি অলরেডি ডিসকাস করলাম যে in a linear reciprocal network the source and response may be interchanged, their values will not change. If you don't change the value of the source, response value will remain unchanged. This can be done. And if this can be done, the network is said to be bilateral, the network is said to be reciprocal. Okay, then I want to now investigate what will be the conditions of the impedance matrix and admittance matrix of the network. If the network is bilateral and linear, that means if the network is reciprocal. So assume that the network is reciprocal and we want to establish some condition for that reciprocal network. In that network, so there are n number of loops. There are many loops, say n number of loops. But what we have done, we have removed all the sources of the network except the voltage source at loop A and say that voltage source is represented by value is represented by ek and say ek value is equal to ek the source has a definite value and that definite value is say e. We are keeping a voltage source at loop k and under this condition I want to measure the current at loop m. সবকটা লুপেই আমি কারেন্ট মেজার করতে পারবো কিন্তু I want to measure the current at loop m. So I can write this equation, loop equation I can write. Loop impedance matrix into loop current vector equal to voltage vector of the source, voltage vector at the loop, that I can write. In this equation, this is non-zero. At the kth loop, this is non-zero. তাহলে আমি কি করতে পারি? আমরা বলতে পারি যে say we can solve for the current vector by taking the inverse of this impedance matrix. কারণ এই একটা z into I equal to v দেওয়া রয়েছে, I solve করতে গেলে obviously you have to take the inverse of z. Since this is the impedance matrix, loop impedance matrix, inverse of that will be the loop admittance matrix. So if you take the inverse of this matrix, loop impedance matrix, the matrix will become the admittance matrix of the loop. In the loop admittance matrix, say elements are like this, ymk, mth row kth column element I am writing ymk. That means it will be y11, y12, y13 the first row like this, 11k, y1m, etc. In the mth row it will be ym1, ym2, ym3 in this way, ymk, yam, mm like this. Okay, so here if I find out the value of im, that means this has been taken inverse, you have taken an inverse of this matrix. So now if the inverse is taken, we can write, that is actually not written here full form, So the current vector will be equal to admittance matrix into voltage vector. So if that is written, now you can find out the expression IM. IM will be YMK EK only, because in the YMK EK, here you have a Y matrix. YM1 E1, that will be 0. YM2 E2 will be 0. Okay. Into YMK EK will be a non-zero. Y say MN EN also will be 0, because only this is the non-zero value remaining. So YMK EK will be equal to the, will be produce a non-zero value, and that value is the current IM. So we can write IM is basically YMK EK. Okay, how this admittance matrix is formed? By taking the inverse of the impedance matrix, and YMK means the mth row kth column of that matrix. Okay, so using this, putting a voltage source at loop K, we are measuring the current at loop M. That current is IM YMK EK. Now you interchange the position of the source and also response. Now say the source is placed at loop M and current will be measured at loop K. Okay, source will be placed at loop M, same source, current will be measured at loop K. তাহলে আমি কি করতে পারি? Same equation I can write. Again I can write the loop equation at Z loop into I loop equal to voltage vector. Now here it will be at loop M. EM will be, value will be EM. Okay. Now to find out the current in the new condition, again you have to take the inverse of the impedance matrix. So expression will be I will be equal to Y into this voltage vector. Okay. In this voltage vector now, EM has a non-zero value. So what you can write? IK. IK now you have to find out. IK will be YKM EM, because IK will be YK1 E1. E1 is 0. Plus YK2 E2. E2 is also 0. Plus YK3 E3. That is also 0. In this way, plus YKM EM. Plus YKN EN. For all the terms it will be, but none of the term will be non-zero. Only YKM EM will be non-zero. So this is how I can find out the expression for current at loop A. Now, according to reciprocity theorem, it says that for a reciprocal network, you can interchange the position of the source and response. Okay. If the source value is not changed, response value also will remain unchanged. So we are not changing the source value. Say source value is made equal to E in both the cases. EK is made equal to E, EM also is made equal to E. If this is true, you can say that IM also will be equal to IK. So reciprocity theorem says that IM will be equal to IK if the network is linear and bilateral. That means if the network is reciprocal, IM will be equal to IK. So in that case, since IM and IK they are equal, YMK EK will be equal to YKM EM. EK is made equal to E, EM also made equal to E. Both are kept same. If we keep both same, the YMK is equal to YKM. YMK is equal to YKM. That means in a matrix, is a loop admittance matrix where mth row kth column of that matrix equal to kth row mth column. Means this matrix is symmetric. That means for a reciprocal network, the admittance matrix, impedance matrix, all these matrices will be symmetric. Or if the network impedance matrix or network admittance matrix, they are symmetric, you can say that the network will be reciprocal. It means that if the impedance and admittance matrices are symmetric, the network is reciprocal. This is what you can say. Is it clear?
Yes, sir.
এর মানে স্যার মানে হচ্ছে এখানে যে নেটওয়ার্কের মধ্যে যে কোথাও যে ডিপেন্ডেন্ট সোর্স কি যে থাকা যাবে না?
না না, থাকা যাবে, কিন্তু রেসিপ্রোকাল dependent source যখন থাকবে, then there is a possibility that network will remain will no longer be reciprocal. There is a chance. Chance কেন বলছি আমরা, কারণ so far we have seen that by introducing dependent sources, network is becoming Z matrix or impedance matrix
asymmetric.
হ্যাঁ, এটা অ্যাসিমেট্রিক হয়। কিন্তু আমরা এইটা যদি আমরা কনসিডার, এটা আগে দেখেছিলাম, কিন্তু in the when we have considered the coupled circuit, you see that in case of coupled circuit, if you write the impedance matrix, okay, when the coupled circuit দেখা যাবে যে there, okay, there the you see that this matrix is symmetric again. Here the effect of mutual
ডিপেন্ডেন্ট সোর্সের পরেও সিমেট্রিক,
হ্যাঁ,
এই যে ডিপেন্ডেন্ট সোর্সের পরেও সিমেট্রিক থাকছে।
পরেও সিমেট্রিক থাকছে। কেন সিমেট্রিক থাকছে? Observe this feature here. কেন সিমেট্রিক থাকে? Can you think of this?
এর কারণ এখানে যে দুটো লুপেই তো সেম এফেক্টটা পড়ছে।
Same effect পড়ছে, because now the dependent sources are placed symmetrically. তাই তো? আগে সেটা ছিল না। Now the dependent sources are placed symmetrically. তারপরে আগে যে ডিপেন্ডেন্ট সোর্স ছিল সেটা কিন্তু অ্যাসিমেট্রিক্যালি প্লেসড,
মিউচুয়ালি ব্যাপারে।
ঠিক আছে, এবার দুটোই রয়েছে, কিন্তু যেহেতু মিউচুয়াল কাপলিং, একটা লুপে থাকতে, একটা ব্রাঞ্চে থাকলে অন্য ব্রাঞ্চে থাকতেই হবে, তাহলে একটা লুপে থাকলে অন্য লুপে থাকতেই হবে, and they are placed symmetrically. Okay, that's why the matrix, impedance matrix becomes symmetric again. So তাহলে ডিপেন্ডেন্ট সোর্স, in presence of dependent source, আমরা বলতে পারি যে a network may lose its symmetrical property or may lose its reciprocal property.
Yes.
Okay, কিন্তু সবসময় যে লুজ করবে তা নয়। It depends upon the presence of the dependent source. If the dependent source is present symmetrically, then again the network will be symmetrical and the network will be reciprocal as well. Okay.
Yes, sir.
But generally, you can say that the condition of the for being reciprocal, the condition to be fulfilled is that Z MK will be equal to ZKM, YMK will be equal to YKM. অর্থাৎ impedance matrix, loop impedance matrix, nodal impedance matrix, loop impedance matrix, যা খুশি হোক, যে কোনো নেটওয়ার্ক matrix will be symmetric matrix for a reciprocal network. Is it clear?
Yes, sir.
Anybody else? Anybody having any doubt? Any question? Anybody who could not understand this reciprocity or any doubt regarding reciprocity theorem?
স্যার মানে নেটওয়ার্কটা যদি অ্যাক্টিভ নেটওয়ার্ক হয় তাহলে তো রেসিপ্রোসিটি থিওরেমটা অ্যাপ্লিকেবল হবে না।
নেটওয়ার্কটা অ্যাক্টিভ নেটওয়ার্ক হলে আমরা নেটওয়ার্কের ইম্পিডেন্সটা কোনটার জন্য কাটছি, নেটওয়ার্কটা ইম্পিডেন্স আমরা যদি প্যাসিভ এলিমেন্টস গুলোই শুধু এই ইম্পিডেন্স ম্যাট্রিক্সের মধ্যে ঢুকছি, সোর্স গুলো এর মধ্যে কিন্তু ঢুকছে না। কোন সোর্স গুলো ঢুকছে? দোজ সোর্স ডিউ টু that means the dependent sources are entering here. Okay, তাহলে ওই ধরনের নেটওয়ার্কে that means the network is passive, sources are external, আমি ওই সোর্স গুলোকে বাদ দিলে যে নেটওয়ার্ক পোর্শন থাকে সেই নেটওয়ার্কটা কি প্যাসিভ, যদি এই প্যাসিভ নেটওয়ার্কে যদি আমি ধরি তাহলে that network is reciprocal if the elements are linear. Okay,
ওকে স্যার।
এবার অন্য সোর্স থাকতে পারে, কাপলড সোর্স, কাপলড ডিপেন্ডেন্ট সোর্স থাকতে পারে। ডিপেন্ডেন্ট সোর্স when they are present asymmetrically, then the network will become it will lose symmetrical property or reciprocity property. Okay, তাহলে ডিপেন্ডেন্ট সোর্স থাকতে পারবে, but they should be present symmetrically. All right.
Yes, sir.
Okay. So next, after this, we may now in a position to consider this superposition. Okay, or we can stop here also, no problem. It is better perhaps I think এটা হতে পারে যে you go through some example of reciprocal network now because this is new completely. I thought that this was done a bit. এই যে যদি জানতাম যে এটা হয়নি তাহলে আমি আরেকটু কারণ এখানে লেখা না থাকলে তো সেটা আমি শুধু মুখে বলে তো নেটওয়ার্ক এক্সপ্লেন করা যাবে না তাহলে it is better if actually you solve some example or see some example of reciprocity, okay, reciprocal network. If you are having any book then it is all right. If you don't having any book then obviously today in these days net is available to you. You give search with reciprocity or reciprocity theorem, you will find lot of examples. Some of this example you study, you solve, and then it is better to proceed to the next step. Because in the next case, what we shall do, I shall have to actually apply reciprocity theorem. The examples that we shall consider uh, next. There, after considering the superposition theorem, superposition perhaps is known to you, তাই তো? Superposition জানা আছে তোমাদের করেছো আগে?
হ্যাঁ স্যার
Superposition is known to you. Since superposition is known to you, it will not be a problem to understand this simply because simply what is additionally here is that we are considering superposition in presence of initial conditions, and again consideration of initial conditions will become a bit problematic now because of the application of that Laplace transform. So এটা একটু লাগবে. Therefore it is better not to consider this example, but more simple examples of linearity or superposition theorem that is already known to you. If required, we shall explain that again. Okay, but this discussion I cannot proceed today because the Laplace transform has not yet been done in that extent. Okay, to that extent. And then actually I shall consider another example where the application of reciprocity theorem will be very much there. And unless you understand the reciprocity theorem properly, then following this example will be a bit difficult. So it is better you go through the reciprocity theorem. Okay, something is I have discussed here from the আমি যতটা লিখেছি সেই অবধি আমি ডিসকাস করতে পারছি because since we are not in the classroom I cannot extend this discussion with more examples or more discussion. আমি আঁকতে পারছি না এখানে. Okay, so it is better if you do some examples, you will practice some examples on reciprocity theorem. Where you will get these examples, you go to Google, give the search as reciprocity theorem or reciprocal network, you will find lot of them. Okay, you go through some examples and also solve some examples on yourself. Okay, on your own you solve some examples and then it will be easier for me to discuss. And if necessary I shall also actually create some document which I can present to you to discuss the reciprocity theorem in a larger extent, and then I can proceed. Okay, so I think it will be better if we not go further today and limit our discussion up to this point, and next class we shall discuss the superposition theorem along with the application of reciprocity and some other, that means network theorems, some examples we are solving, where in the next example actually there will be application of reciprocity along with some other theorem. Okay, so it is better if we stop here, and up to this if you have any question you can make those questions, you can discuss those questions. Okay, আর কি